Hey everyone, so we are now going to do 1.5a. So 1.5 is split into two sections. The first one is polynomial functions and complex zeros. So note that complex zeros or complex refers to both real and non-real numbers. So now we are talking about imaginary. So here we have the first example, zeros, intercepts, and linear factors. If we have p of a is equal to 0, then a is what's called a root or a zero of the function p. We have an x-intercept at a comma 0, and if a is a real number, then x minus a is what's called a linear factor. So in my example here, what I want to do is find the x-intercept. So to figure that out, what I want to do, I can either graph it in my graphing calculator, or I can do it the long way, which I'm going to do this time, which is just by factoring. So the first thing I want to do, all three of these terms have an x in common. So I'm going to factor out that x, which leaves me with x squared minus 2x minus 8. And then from here, I can kind of do a quick little shortcut. So I can't forget about that x on the outside. What I'm going to do is I'm going to open up two sets of parentheses. Now, because I have that x squared, they're both going to have an x. I use my first sign, which in this case is a negative. And then what I do is a negative, and I combine it with my second sign. So a negative times a negative gives me a positive. The last step I need to do is figure out what factors of 8 combine to give me this 2 here in the middle. Well, I only have 1 times 8 and 4 times 2, and I'm pretty sure 4 times 2 is the winner. Now, because I want a negative 2, my larger number of the factors is going to take the sign that I want. So that's going to be 4 plus 2. Now I can say my x-intercepts are at x equals 0, right? That's my first x. Then I can have x equals a positive 4, because what I want to do is set them equal to 0. So x minus 4 equals 0. And when I solve for x, it's going to be a positive 4. And the same situation with that 2, it's going to be at x equals negative 2, because x plus 2 equals 0. Okay, so those would be my x-intercepts. You guys can ask me these questions again on Tuesday if we're a little bit confused. Now, multiplicity. If a linear factor x minus a is repeated n times, the corresponding zero of the polynomial function has a multiplicity n. If the real zero a has even multiplicity, then the graph will bounce off the x-axis at x equals a. That's a bunch of words. Basically, what this tells me is that, if, for example, in my example right here, I have x plus 1, 2. All that means is that x plus 1 has a multiplicity of 2. That means x minus 3 has a multiplicity of 3, and x plus 4 has a multiplicity of 1. You don't write when it has a multiplicity of 1, right? If you multiply something by 1, you don't say it's times 1, you just say the number, okay? And then in regards to the last part, if it is an even multiplicity, so I'm going to go back to this x plus 2 or x plus 1 multiplicity of 2. That means that I have a 0 at negative 1. And what my graph is going to do is it's actually going to touch the x-axis, but not cross. That's what it means when it says bounce. Okay. Now, at x minus 3, which means it's going to be a positive 3, my multiplicity is an odd number, so it's going to pass right through the x-axis. And the same thing with that x plus 1. 1 is an odd number, so it would pass right through that. Now, complex zeros, a polynomial of degree n has exactly n complex zeros when counting multiplicities. If there are any real zeros, they always come in conjugate pairs. This means that there are either no non-real zeros or an even amount. So remember, complex zeros are going to have that I, that imaginary aspect, okay? Now, I have here a chart. In this first one, we have the quadratic degree of 2. I have a regular function. It hits the graph twice. So I have 2 real numbers and a quadratic. So let me give you the hint. If I have a polynomial the degree of my polynomial is going to tell me how many zeros I have. Okay, so if I have 2, that means I'm going to have 2 zeros, okay? Whether they are both real or imaginary, that's what I need to figure out, okay? But I will know there are going to be at least 2. Now, if I just realize what I just read, I can either, in a quadratic function, I can either have no non-reals or I have to have 2, okay? So in these first 2 examples, I have 2. Now here I have that. I can easily see 2 x-intercepts, right? 2 zeros. On this one, notice again, my graph is going to bounce, meaning that it has a multiplicity of 2 at this point. So it does have 2 real zeros. Now here, I don't cross or touch the x-axis. When I don't cross or touch the x-axis, that means I'm having a complex zero. I'm having a non-real, okay? When it comes to cubic, right, I have 3. I can have 3 zeros, so I can have 2 non-real and 1 real. That's the only situation, right? So in this case, I have 3 reals because I hit the graph here, I hit it over here, and I hit it one more time. Here, I hit, and the second one, I hit the graph once, and then notice I don't touch it again, meaning I have 2 non-reals and 1 real. And then here, once again, I'm crossing and I'm doing a bounce again. That means a multiplicity of 2. So those are 3 real zeros, okay? Now, non-real zeros. If a plus bi is a non-real zero of polynomial p, then its conjugate, a minus bi, is also a 0. So remember, the conjugate is going to be changing that sign. So I have here an example, which is -3 plus 6i. So what's going to happen is I'm going to write -3 minus 6i. And that is my conjugate. That means that these two are zeros of whatever polynomial I'm talking about, okay? Now, the last thing in this section is successive differences to find the degree of a polynomial. That is something that I would prefer to do on Tuesday because it is a lot of work and I feel like we'll have some questions about it. So I will want to go over that with you guys on Tuesday. So for that, enjoy the rest of your day and happy studying.